Here's a strange thought experiment. Somewhere out there, right now, there's a place where the normal rules just stop working. Time slows down, space folds in on itself, and light, the fastest thing in existence, simply can't leave. We call it a black hole, and for most of history, it was just a shape on a chalkboard, a solution to an equation nobody was sure actually existed. Now we've photographed one. We've watched stars get torn apart by one, and yet the strangest part is still a mystery. Nobody actually knows what happens to something or someone that crosses inside. So in this video, we're not just going to look at a black hole from a distance. We're going to walk through what the science says would actually happen if you got close enough to fall in step by step, moment by moment. And along the way, you might start to notice something unexpected about the universe you already live in. Let's start with something important, because almost everyone gets this wrong at first. A black hole is not really a solid object, the way a planet or a star is. It's closer to a place, a region of space where gravity has grown so strong that it breaks the normal rules of space and time. And here is the one fact that matters most. Once you cross its edge, you can never leave. Not even light can get back out. Anything that falls in is cut off from the rest of the universe, permanently. So how does something like this even form? It usually begins with the death of a giant star. For its entire life, a star is holding a tug-of-war between two forces. Nuclear reactions in its core push energy outward, trying to make it expand. Gravity pulls everything inward, trying to make it collapse. As long as the star has fuel to burn, these two forces stay balanced, and the star holds its shape. But when the fuel runs out, the outward push suddenly stops, and with nothing left to resist it, gravity wins. The star falls in on itself. It's hard to appreciate how extreme that collapse really is, so let's put real numbers on it. Our sun is more than 100 times wider than Earth. If you crushed it down into a black hole, all of that would shrink to a ball just about 6 kilometers across, small enough to sit inside a single city. And here's the unsettling part. It would still carry every bit of the sun's gravity. Do the same thing to Earth, and our entire planet would collapse to less than 2 centimeters wide, smaller than a marble. That's how tightly the matter gets packed. From the outside, though, scientists actually understand these objects rather well. We can measure how big they are, calculate their mass, and watch the way they bend the light of stars sitting behind them. A few years ago, they went one step further and did something that sounded impossible. They took an actual photograph of a black hole. No single telescope on Earth is powerful enough for that, so they linked radio telescopes from all across the planet into one network, turning the whole Earth into a single telescope. The image they produced showed a dark circle wrapped in a glowing ring of hot gas, swirling around the edge just before vanishing. And this is the important thing. That photo is not a guess or an artist's drawing. It's a real observation. Then, in 2024, the same team turned their attention to Sagittarius A, the enormous black hole sitting at the center of our own galaxy. For the first time, they mapped out its magnetic field and found it arranged in a neat, orderly pattern, strikingly similar to the one around a far larger black hole in a distant galaxy called M87. Two black holes, wildly different in size, behaving in the same way. Here's something stranger still. No matter how a black hole forms, whatever kind of star fell in, whatever it was made of, every black hole in the universe can be completely described using just three numbers: its mass, how fast it spins, and its electric charge. That's it. Scientists have a joking name for this. They say black holes have no hair, meaning they carry no other distinguishing features. Whatever falls in seems to lose every trace of its individual identity. This line of thinking is much older than you'd expect. Back in the 1780s, an English scientist named John Michell first pictured a star so dense that its own light couldn't escape it. The idea was so far ahead of its time that the world simply forgot about it for over 100 years. Our modern understanding only really began later, when Karl Schwarzschild worked out part of Einstein's equations. Remarkably, while serving on the front lines of World War I. And yet, for all of that progress, everything past the edge of a black hole remains completely unknown to us. So let's face the big question head-on. What is really at the bottom of a black hole? The honest answer is that there is no bottom, the way a well has a bottom. There's a center, and what sits at that center is one of the largest unsolved mysteries in all of physics. Keep that question close, because everything else in this book is building toward it. The first real boundary you'd meet on the way down has a name: the event horizon. It isn't a wall. There's nothing solid there to crash into. In fact, if the black hole is large enough, you could cross it without feeling a single thing. That's because the event horizon isn't a physical object at all. It's a line, a mathematical boundary. It marks the exact place where gravity becomes so strong that escaping would mean traveling faster than light. And since light moves at about 300,000 kilometers per second, and nothing in the universe can go faster, that line becomes a true point of no return. Cross it, and there is no path back. Not a difficult path. No path at all. What's curious is that the size of the black hole completely changes what crossing that line is like. Around a small black hole, one roughly the size of a city, you'd feel the danger long before you ever reach the edge. But around a truly giant one, the kind at the center of a galaxy, with an edge millions of kilometers across, the pull is spread out so gently that you could drift right across the boundary and notice nothing at all. And that quietly opens a very strange possibility. One we'll return to at the very end of this book. It may be that you are inside a black hole at this very moment, with no way of ever telling. For now, we've managed to photograph the doorway. What lies on the other side of it is still a complete mystery. So let's keep falling and find out what happens next. Before we go any deeper, we need to clear up a couple of things, because the name black hole quietly tricks us into believing things that aren't true. Start with the word hole. When you hear it, your mind reaches for something familiar: a tunnel, a pit, an opening you could fall into and come out the other side of, somewhere new. It's a natural thing to assume. But it's the wrong picture entirely. A black hole is not a tunnel, and it's not a doorway to another place. It's simply a spot where so much matter has been crammed into so little space that nothing which drifts too close can ever climb back out. And the black part fools us too. It isn't an opening into somewhere else. It's just the absence of light, plain and simple. No light is coming back from that spot to reach your eyes. So when you look at that famous dark circle in the photograph, you are not looking down into a pit. You're looking at a shadow, the mark left behind because light fell in and never returned. It's a neat lesson in how a single word, whole, can quietly shape the way we see something, long before we stop to check whether the picture in our head is even right. Here's a second idea worth untangling, and it's one a lot of sharp people land on. If a dying star collapses, why doesn't it just end up as an incredibly dense ball at the center? Something like a neutron star, only heavier. That's a genuinely good question, and it's worth taking seriously. A neutron star really is one of the densest things the universe has to offer. Picture a ball roughly the size of a city, packed so tightly that a single teaspoon of it would weigh about as much as a mountain. But, and this is the key, it still has a surface. It still holds itself together. The particles crammed inside it push back against gravity hard enough to keep from being crushed any further.
A titanic shockwave rips the star
There's
apart,
a floor.
leaving behind a perfectly
There's
black
ground.
event horizon.
A black hole is what happens when even that fierce resistance finally gives out. Once a collapsing star's core crosses a certain mass, nature simply has no force strong enough to halt the collapse. Nothing pushes back hard enough. So it keeps falling inward, past the point where any surface could survive. And that is the real difference between an ultra-dense star and a black hole. One of them still has ground you could, in principle, stand on. The other has no surface anywhere. It has traded that surface away for the one-way boundary we met in the last chapter, the event horizon. And what about wormholes? Those tunnels through space you've seen in films, linking a black hole to some far-off corner of the universe. It's one of the most famous ideas attached to black holes, and I promise we'll come back to it properly later. But here's the plain truth, said early so it doesn't mislead you. A wormhole is only a possibility that shows up in the mathematics. Nobody has ever seen one. Nobody has ever proven one exists. So for now, we set it gently aside. Which leaves us with what we actually know for certain. A black hole is not a tunnel you fall through, and it's not a giant solid ball you could land on. It is something stranger than either of those, something our everyday words were simply never built to describe. And since it's neither a tunnel nor a star with a surface, there's only one way left to learn what it truly is: to keep falling, and to watch closely what happens next. So you've crossed the edge, and now the fall starts to change you. Here's why. Gravity gets stronger the closer you are to something massive. That means if you're falling feet first, your feet are always a tiny bit closer to the center than your head. So gravity pulls your feet a little harder than your head. Near Earth's surface, this difference is way too small to notice. But near a black hole, This difference grows and grows without limit. Your feet get pulled down faster than your head, so your whole body starts stretching longer and longer, while also getting squeezed in from the sides. Scientists have a fun name for this, spaghettification, because you'd basically get pulled into a long, thin noodle shape, like spaghetti. Here's something surprising that flips what you'd expect. You might think bigger black holes are more dangerous, but when it comes to stretching, it's actually the opposite. Around a small black hole, gravity changes so sharply from your head to your feet that you'd be torn apart before even reaching the edge. But around a huge black hole, like the ones at the center of galaxies, gravity changes much more gently across your body. In fact, for the biggest black holes, the stretching force when you cross the edge is actually weaker than normal gravity on Earth. You could cross the edge completely fine, and only start getting stretched apart much deeper in, around 130,000 kilometers from the center. This isn't just a theory. Scientists have actually observed it happening. Sometimes a star wanders too close to a giant black hole, and telescopes catch a sudden burst of light as the star gets pulled apart into a long stream of glowing gas. Scientists have even tracked one star that survived getting close once, swung back out into space, and then came back for a second pass. So this stretching effect is real. It's been observed and measured. But getting stretched into a noodle is only half the story. Now we get to the strangest part of falling into a black hole. Time itself starts acting weird. What happens depends entirely on who's watching. If you're the one falling in, everything feels normal and happens quickly to you. But if a friend is watching from far away, they'd see something totally different. You would appear to slow down more and more as you got close to the edge. Your movement would seem to freeze. Your image would fade and turn redder, until it looked like you were just hanging there forever, never actually crossing. So which is true? Do you get crushed, or do you freeze in time forever? The honest answer is both and neither. It depends on where you're standing. From the outside, you look frozen at the edge forever. From your own point of view, you sail right through and keep falling. Two completely different stories, and both are true at the same time. This isn't just a weird fact. It's actually connected to one of the biggest unsolved mysteries in physics. If people outside the black hole never actually see you cross the edge, but you clearly do cross it from your own point of view, then where does everything that falls into a black hole actually end up? Keep that question in mind. We'll come back to it once we learn how black holes can slowly disappear over time. Let's stay with this idea of time for a while, because it's one of the most astonishing, mind-bending parts of the entire journey. Here's the thing most people never realize. Gravity doesn't only pull on objects. It also slows down time itself. And the stronger the gravity, the stronger this effect becomes. This isn't science fiction. And it isn't a thought experiment. We measure it in ordinary life, every single day. The GPS satellites that help your phone find its way have to account for a strange fact. Time runs very slightly faster for them, way up above the Earth, than it does for us down here on the ground. If engineers ignored that tiny difference, your maps would drift off by kilometers within a day. So take that everyday effect and turn the dial up as far as it will go. As you fall deeper toward a black hole, time slows down so drastically for you that the rest of the universe appears to speed up. Someone hovering just outside the edge could, in principle, watch the entire future of the cosmos unfold, like a film on fast forward. Stars igniting and burning out, whole eras of history rushing past, all in what feels to them like just a handful of moments. Now, this is exactly where people tend to get tangled up. So let's be very clear about who feels what. To you, the one falling inward, your own watch keeps ticking along perfectly normally. Second by second, nothing feels off. You never actually sense time slowing down. The difference only appears when someone sets your clock beside a clock far away and compares the two. And then the gap turns out to be enormous. Time isn't breaking here. It isn't malfunctioning. It's simply running at wildly different speeds in different places, all at once. And while all of that is happening, the view around you would turn into something genuinely unrecognizable, because the black hole's gravity is strong enough to bend light itself. Light from stars sitting directly behind the black hole gets curved around its edges and arrives at your eyes anyway, as if the black hole were bending the scenery around a corner. So the darkness ahead of you would appear wrapped in a warped, glowing ring made from the light of the universe behind it. And this isn't an artist stretching the truth for effect. NASA has built careful, detailed computer simulations of exactly this. They show the entire sky folding into rings around the black hole, the same image echoing outward in layer after layer around the dark center. Look one way, and you'd see a twisted ring of light. Look the other, and you'd see a growing pit of pure nothing. And as you fall further, the light itself begins to die. That bright circle of the universe above you shrinks and dims. Its light gets stretched thinner and thinner, draining away its energy as it struggles against the black hole's pull, shifting from white to red, and finally fading out altogether. One by one, the stars wink out. The bright circle overhead narrows to a single point, flickers once, and then it's gone. And for the first time anywhere, you would be in a place with no light at all. Not because there's nothing nearby to glow, but because light can no longer reach you from anywhere in existence. It's a kind of darkness that has no equal on Earth. Not simply the lamp is switched off, but a complete severing from the rest of the universe. This is a good place to stop and catch our breath, because we've arrived at an important line. Everything we've walked through up to this point rests on physics that scientists can genuinely test, measure, and trust. From here onward, we cross into territory where even our very best theories begin to fall apart. Before we travel all the way to the center, there's a puzzle we have to sort out first. It nags at a lot of people, and being confused by it is completely fair. It really does sound like a contradiction. We keep insisting that nothing escapes a black hole, not even light. And yet you may also have heard that black holes slowly leak energy and, given enough time, fade away entirely. Set those two statements side by side, and they seem to flatly disagree with each other. So let me walk through how both can be true at once, because the resolution is one of the most beautiful ideas in all of modern physics. It comes from Stephen Hawking, who worked out that black holes aren't perfectly black after all. They give off an unbelievably faint glow, which we now call Hawking radiation. And to see where that glow comes from, we first need one strange fact about empty space. In quantum physics, empty space is never truly empty. It's constantly fizzing with pairs of tiny particles that flicker into existence for the briefest instant and then vanish again, borrowing a scrap of energy and paying it straight back. This is happening everywhere, all the time, in the air in front of your face right now. Normally, it's so fleeting that we'd never know. But at the very edge of a black hole, this ordinary fizzing takes a strange turn. Every so often, one particle of a pair slips across the edge and falls in, while its partner shoots off outward into space instead. That escaping particle carries away a small amount of energy, and to balance the books, the black hole has to cover the cost by giving up a tiny sliver of its own mass. Here's the piece that resolves the whole puzzle. Nothing is actually escaping from inside the black hole. The particle that gets away was created just outside the edge, in that restless fizzing space, not deep within. So the old rule, nothing escapes from inside, stays perfectly intact. The black hole simply shrinks, little by little, as it keeps settling this energy debt. And when I say little by little, I mean at a pace that's almost impossible to grasp. A black hole the mass of our Sun would take roughly 10 to the 64th power years to fully evaporate. That's a 1 followed by 64 zeros. To give that some scale, the entire age of the universe so far, every year since the Big Bang, is essentially a rounding error next to it. Now here's a twist that runs against everything your instincts expect. With ordinary objects, bigger things tend to be hotter and radiate more. With black holes, it's flipped completely. The giant ones are extraordinarily cold and fade the slowest of all, while the small ones are the hottest and burn away the fastest. And it feeds on itself. The smaller a black hole gets, the hotter it grows, and the faster it fades. Which means its final moments would be far more violent and dramatic than the long, quiet stretch of its life that came before. But this slow leak of energy opens the door to one of the deepest puzzles in science. the information paradox. Quantum physics insists that information about anything falling into a black hole can never be truly destroyed. It has to end up somewhere. And yet, if the black hole eventually evaporates away to nothing, then where on earth did all that information go? For decades, this looked genuinely unsolvable. And I'll be straight with you, it still isn't fully solved even now. But it's no longer a dead end either. In recent years, scientists have made real, concrete progress, with new mathematics hinting that the information isn't lost after all. Fresh research papers, some as recent as 2024, keep putting forward new ways to crack it. This is a mystery being actively fought over right now, at the very frontier of physics. And now we've arrived at the center, the place this entire journey has been leading us toward. From the very first page, according to Einstein's equations, everything that has ever fallen into a black hole, a whole star, sometimes far more than that, gets crushed down into a single point of zero size and infinite density. That point has a name: the singularity. But I have to be honest with you about what that word actually means, because it's easy to mistake it for a confident answer, when it's very nearly the opposite. When our equations start producing infinity, the way they do right here, that isn't nature handing us some profound truth. It's our theory quietly admitting defeat, telling us we've pushed it past the point where it can explain anything at all. And this isn't some fringe or hand-wavy claim. Back in 1965, the physicist Roger Penrose proved mathematically that once matter collapses past a certain threshold, the formation of a singularity becomes essentially unavoidable. There's no clever way around it. That work was considered so significant that it earned him a share of the Nobel Prize in Physics in 2020, more than half a century later. And in case any of this is starting to feel like nothing but chalk on a blackboard, hold on to this. In 2015, scientists directly detected ripples in the fabric of space, gravitational waves, set off by two black holes slamming into each other far across the universe. These aren't abstractions. They are as real as the floor beneath your feet. We even know that black holes spin. Back in 1963, the mathematician Roy Kerr worked out the equations for a rotating black hole, and nearly every real black hole we've ever observed turns out to be spinning, often at staggering speeds, hauling space and time around with it, the way water twists as it drains from a sink. Here's a question a lot of thoughtful people ask, and it's a good one. If all the matter really does get crushed into a single point with essentially nothing left there, then what is still producing all that gravity? Shouldn't it just switch off? It's a sharp question, and the answer is subtle. The gravity was never coming from a lump of stuff sitting at the center. It comes from the mass and energy that fell in, which leaves a permanent imprint on the shape of space and time around the black hole, whether or not any solid object still remains at the middle. In fact, most physicists don't believe the singularity is truly real at all. They treat it more like a placeholder, a warning light on the dashboard, telling us our current theory has run out of road. To actually understand what sits at the center, we'd need a deeper theory that unites gravity with quantum physics. And we simply don't have one yet. There's one last strange thing worth knowing about this final stretch of the fall, because it explains why there's genuinely no escaping the center once you're inside. Out here in ordinary space, you can move however you like: left, right, forward, back. What you can't do is stop tomorrow from arriving. Time only flows one way, and no effort of yours can turn it around. Once you cross the edge of a black hole, space and time essentially trade places. The center stops being a location somewhere ahead of you in space and becomes a moment somewhere ahead of you in time, as unavoidable as next week. That's the real reason no rocket engine, however powerful, could ever swing you back around. Reaching the center is no longer like traveling to a destination. It's more like waiting for the future to arrive, with no say in the matter. Nobody has yet built that deeper theory. So at the very bottom of the fall, science doesn't hand us a tidy final answer. What it hands us instead is an honest, thrilling question, and a few bold ideas about how we might one day answer it. So if almost nobody believes there's really a point of infinite density waiting down there, then what might actually sit at the center instead? Scientists have put forward several bold ideas over the years. Let's walk through three of the most fascinating ones, each attempting, in its own way, to replace that broken infinity point with something that genuinely makes sense. Idea number 1. The fuzzball. This first idea does something drastic. It gets rid of the singularity entirely. It grows out of string theory, which proposes that the smallest building blocks of everything aren't tiny points at all. They're tiny vibrating strings of energy, each one humming at its own pitch. Apply that to a black hole, and the whole picture shifts. Instead of empty space wrapped around one deadly central point, the entire interior would be filled. A dense, tangled knot of these strings, packed solid all the way out to the edge. Scientists call this a fuzzball. And in this version, there is no bottomless pit, and no singularity lurking at the heart of it. You'd simply meet the surface of the fuzzball itself, far more like touching down on a very strange kind of star than plunging into a hole. It's an elegant idea, but it comes with a price. You have to give up the notion of a clean, sharp edge entirely. And it's worth stressing that this remains only a proposal. Nobody has proven it's the truth. Idea number 2. The wormhole. Now for the one you've probably been waiting for. The wormhole. Tucked away inside Einstein's own equations is a structure that could, at least on paper, stretch out into a kind of tunnel, a shortcut. a passage linking to another region of our universe, or perhaps even to a completely different one. For a long time, scientists brushed this aside as little more than a curious quirk of the math, since a tunnel like that would very likely snap shut almost the instant it formed. And I want to tread carefully here, because wormholes are exactly the sort of idea that gets wildly overhyped. Nobody has ever actually found one. The closest anyone has come was in 2022, when physicists used a quantum computer to simulate a wormhole-like system. That's a genuinely intriguing hint that the mathematics tying gravity to quantum physics is onto something real. But it is a very long way from an actual tunnel you could ever travel through. Idea number 3, the baby universe. And now the boldest idea of the three, the one that somehow makes black holes sound almost gentle. The physicist Lee Smolin proposed that as matter collapses toward the center, quantum effects might halt the crushing at the very last instant, just before a true singularity can form. And rather than being crushed out of existence, the matter rebounds outward, blossoming into a brand new region of space and time, complete with its own Big Bang. In this telling, the violent death of one universe becomes the tender birth of another. Smolin pushed the idea even further, suggesting that each new baby universe might come into being with slightly different laws of physics from its parent. And over countless generations, the universes that happened to be especially good at producing black holes would become more and more common. If he's right, then every black hole scattered across the night sky could be the seed of an entirely new universe. And our own universe may itself have been born inside a black hole, belonging to some far older one. None of these three ideas can be tested with the technology we have today, and every one of them might turn out to be wrong. One more twist: the firewall problem. Before we move on, there's one final idea worth putting on the table, because it lays bare just how deep the disagreement in physics really runs. Some scientists argue that the edge of an older black hole may not be the calm, gentle boundary we described earlier at all. It might instead be a scorching wall of energy, a firewall, that would obliterate anything the moment it touched. That firewall idea comes straight out of quantum mechanics. But the peaceful, uneventful crossing we described earlier comes straight out of Einstein's theory of relativity. And here's the deeply unsettling part. Our two best, most thoroughly tested theories flatly disagree about what would actually happen to you at the edge of a black hole. And to this day, nobody has found a way to settle the argument. But whichever of these ideas eventually proves true, they all share one thing in common. Not a single one of them is willing to accept infinity as the final answer. That last idea, that a black hole might give birth to an entirely new universe, leads us to a question that sounds like pure science fiction, yet grows straight out of real physics. Could we already be living inside a black hole right now? The seed of this thought is something called the holographic principle, and it came directly out of studying black holes. Scientists noticed something deeply strange. The maximum amount of information a black hole can hold doesn't depend on its volume, on how much room there is inside it. It depends on the area of its outer edge, its surface. It's as though everything that ever tumbled into the black hole ends up written onto that flat, two-dimensional boundary, like data etched onto a single enormous cosmic hard drive. And taken to its logical extreme, this idea suggests something that's genuinely hard to swallow: that the solid, three-dimensional world all around us, everything we touch, everything we move through, could actually be a kind of projection. It's true information stored on some distant, flatter surface far away. The hologram sticker on a credit card is a good way in. It's nothing but a flat, two-dimensional image, yet tilted in the light, and a full three-dimensional picture seems to leap out toward you. The holographic principle proposes that our entire universe might operate on the very same trick. Everything that feels so solid and three-dimensional to us being, at bottom, information stored on a distant, flatter surface. And the truly dizzying part is that from the inside, we could never tell the difference. Now stretch that thought across the whole cosmos, and an even larger question emerges. Could our entire universe be sitting inside a black hole that belongs to some bigger universe outside our own? Could the far edge of everything we're able to observe actually behave like a black hole's boundary, only viewed from the inside, looking out? And this isn't purely armchair speculation, either. In 2025, a study using images from the James Webb Space Telescope found that roughly 2/3 of the galaxies examined appeared to spin in the same direction, when you'd normally expect something much closer to a 50-50 split. One possible explanation, published in a respected astronomy journal, is that the entire universe might be slowly rotating. And a slow, universe-wide spin is exactly what you'd expect if the whole thing had been born inside a spinning black hole. I want to be careful and honest with you here, because this is the most speculative ground we've stepped onto, and it would be all too easy to oversell it. It's one interesting result, and one possible explanation among several. It is not a proven fact. And you may already be forming a sharp objection, one a lot of clever people raise right about now. If we really were trapped inside a black hole, shouldn't everything be collapsing inward, rather than expanding outward, the way we actually observe the universe to be doing? That's an excellent question, and in all honesty, we don't fully know the answer yet. But rather than treating that as a failure, I find it genuinely wonderful. To stand right at the edge of what we understand and be able to say, plainly and without embarrassment, we don't know yet. That isn't a defeat, It's an invitation, a door left open, waiting for someone to keep exploring. So we have fallen all the way down, past the edge, through the stretching and the bending of time, into the darkness, and right up to the very center, only to find that the deepest place in the cosmos is still keeping its secret. And perhaps that is the most honest place to end. We will almost certainly never send a probe into a black hole and get an answer back, because the whole point of that edge is that nothing returns. And yet, we keep falling toward these objects in our minds, building idea after idea, precisely because the inside of a black hole seems to be where the story of everything might be hidden. Whatever truly waits at the center, whether it is a wall of fire, a tangled ball of strings, a tunnel to somewhere else, or the first spark of a universe waiting to be born, it has held on to its secret, the way it has held on to everything that ever crossed its edge. What I find remarkable is that the further in we traveled on this journey, the more the questions changed. Near the edge, we could still lean on physics we can test and measure, but by the time we reached the center, our finest theories had quietly run out of road, and every confident answer dissolved into an honest, open question. That is not a weakness of the science. It is the science working exactly as it should, showing us precisely where the map ends and the unexplored begins. To ask what is inside a black hole turns out, in the end, to be almost the same as asking where we ourselves came from. The deepest place in the universe is still dark to us, and still we keep falling toward it, and we keep trying to understand. And maybe that is the real reward of a journey like this. Not a tidy answer written on the final slide, but a sharper sense of just how much wonder is still waiting out there, and how lucky we are to be the kind of creatures who get to ask about it at all. So I would love to hear what you think. If you had to choose, what do you believe is really waiting at the center of a black hole? A wall of fire, a doorway to somewhere else, or the seed of an entirely new universe? Let me know, and let's wonder about it together.